Let's get the camera situated. I don't know why it's not synced. Oops, that's not good. All right, so I'm gonna get a water first. So we're celebrating 500,000. Jesus, that's just such. That's I know there's a lot of channels that get way more than that, but I just think that's pretty dang awesome. That we got 500,000 views, and we're actually up to 7,600 subscribers right now, which is pretty awesome. And it looks like you are the only one in the stream. I can't really see that chat. I have like the weirdest camera setup ever, but yep, you're the only one in the chat so far. Let's see. All messages are visible. Okay, yeah, that's what I want. So I want to see any message that anyone brings up. Yep, so we're celebrating 500,000 views, which is pretty dang cool. So what I want to do here is to answer any of your questions about the class or the channel or what we want to do on the channel. We can go over some problems if you want. I'm sure there are quite a few people who are taking my class right now. Just wanted to say that your videos on CFGs and PDAs really helped me get a 10 on my midterm. I hope that's out of 10 or something small, but not out of 100 or something. Because if my videos helped you get a 10 out of 100, well, I didn't help that much, but hopefully you did well. Thank you for your support and watching the videos on the channel. So if anyone has any questions, I'm happy to field any of those. If you want to actually support the channel further, there are links in the video description. If you want to donate to the channel, you absolutely never have to, but if you want to, they're there. It's just a big coincidence. My teacher also uses the Sipser book. Yeah, so the Sipser book is a great resource. In fact, next semester we're planning on pseudo using the Sipser book because it's just so widely used. And in fact, my channel is based off of the Sipser book mostly. I eventually want to write my own book, and there are certain developments that are happening right now that a book may be forthcoming, but there's still a long way for that. You do have a video, you have an idea for next videos, that's feel free to send it off to me. I'm not sure. I wish I can have the chat stay there. Oh, that's really annoying. Remember to guard your privacy and abide by your community guidelines. Hopefully theory of computation doesn't violate the YouTube community guidelines. Yeah, so 500,000 views and 7,500 subscribers. In fact, we're up to 7,600 right now. If we get up to 10,000, then I can give, I can offer merch. So like we can design shirts and things and put it into the, have it available under the videos. There are actually links in the video description of existing shirts. I believe they're still up, and I don't think anyone has ever bought one, but they're available if you want to use them. All right, I'll be right back. We have a midterm on Turing machines, and the final exam consists of proofs. So that is kind of weird. You usually kind of want to break it up into the main sections, like regular languages would be one test, then context-free languages would be another, decidability would be one, and then like the final exam or something. You typically don't want to have it too staggered out because the last bit of the class is usually the hardest part in terms of students' ability to understand proofs and things. I have my iPad here, and I didn't really charge it because I didn't plan ahead here. Can I actually see the chat at the same time? Let's try this. I'm being an old man already right here. All right, let's see. Let's see can I go to my channel? That'd be good. Channel. And thanks for all of your support, everyone who's watching. Oh, okay, I can see it. Okay. Why is the sound on? All right. All right, so that's good. Okay, so if anyone has a problem you want to see solved, we can absolutely do it right here. That's why I'm doing it in front of the board here. If you have like a pumping lemma question or context-free grammar question, we can certainly do those. And if anyone else is in a class like this, feel free to send the channel out to them, or maybe this live stream if you want them to see a problem solved. I know a lot of people are struggling in the class right now because I'm on a Discord and I see people are. Hi, Just FPGA. I hope that's not your real name. Glad to see you watching. All right. What kinds of questions do you want to see solved? And I can also make up some questions too. If none of you have any questions whatsoever. You're the man. Thank you. Considering that there are several other billion men in the world, I'm probably not the man. Or I'm not the man in the sense of people selling their souls to the man or whatever. So hopefully you mean that in a positive tone. All right, so enough celebration. Time to do some work. Congrats, man, good work, thank you. So what would be a good problem? Will there be any videos on proofs? I have many different pumping lemma proofs. There's a playlist in the channel. Appreciate your videos, thank you. Thank you, Ryan, for that. Or Ryan, however you spell that, pronounce that. Sadvik, thank you for your comment. I was on my way to my theory of computing class, but your 12th course, 12-hour course, and videos helped me score 97%. Oh, that's awesome. Good to hear. Thank you for your support. All right, so let's see, what would be a good one? So let's consider this language. So let's consider a language L. So this will be a pumping lemma style proof. So this is one that I actually offered on a midterm a while ago. So it's going to be strings of the form 0 to the I, 1 to the j, such that I is less than the square root of j. So in other words, I want all the strings where and in fact we can set this equal, it doesn't really matter. So here, this is saying that there are a lot more ones than zeros. So if we have the string like, let's say, 3 zeros in here at the beginning, then I must have at least 9 ones in a row. So 3, 6, 9. So this string, because there are 9 ones and 3 zeros, that is in L, because it obeys that criterion. And then if I change that to 4 zeros, then that's not an L, because the number of ones must be 16. So feel free to put into the chat whether or not you think that this language is regular or not. So can I make a DFA, NFA, regular expression, whatever, for this particular language? So what do you all think? Can't really stay and see, but I want to thank you for your one. Thank you very much. What was your name? Matt Brott. Thank you very much. So what do we think? Is this thing regular or not? And if you want to annoy your instructor, whenever you get a yes/no question, answer maybe. So the answer to this is maybe. But really, what do you think? Yes or no? Yes or no? Not getting any answers here. So maybe this one seems quite tricky. So I'll go ahead and give away the answer. For $9.95 a month. Kidding. So this thing is not regular. Okay. So just FPGA, it is. Sorry, no, it isn't. So the main reason is that so you can actually formalize what I'm going to say, but I'm just going to give an informal explanation. Then we'll actually prove it. So the main reason is that these runs of zeros and ones, the number of zeros and ones, they rely on each other, but they rely on each other basically. That's the main reason, and they rely on each other in a non-trivial way. So if we had something like I plus j is odd. If I can spell odd, that'd be good. So in some sense, in this case, I and j are related to each other. But it's a little different here because it's kind of like a loose connection between them. So like here, there are only really 4 possibilities. And so we can actually keep track of those possibilities. Whereas over here, we have a lot more possibilities. That doesn't mean that it's not, that's the reason why it's not regular, but it happens to not be regular for that reason in this case. So, all right, so I saw a few more comments come in, but I didn't get to read. Because we can't make a finite machine that processes strings of size n. So Thunder Turner, that's not the actual reason, because any DFA or whatever should be able to handle any string of any length, even though it is finite in size. And that's one of the nice things about this subject, is that you can deal with infinities really easily with just a finite size object. You can represent an infinite set of things. So proof by pumping lemma. All right, so you can prove this in a number of ways. You can use the pumping lemma, which is what I'm going to do here. You can use the Myhill-Nerode equivalence relation. That's another way you can go. Is it context-free? Yeah, this is not context-free either. I think it'd be a lot harder to prove that it's not context-free, and that would get this, but I just want to get not regular here. Okay. So and that actually leads to something important in mathematics and in computer science. When you want to prove something like this, if you try to prove something that is more general that automatically proves this, then that's good. And that's actually the result of something called Rice's theorem, which is this result which you don't have to use, but it proves a lot of things for you. But in some cases, the more general proof is a little harder to do. And in fact, some of the research that I'm doing right now, the more general proof is basically impossible to do, but in a specific case is really easy, or easier in some sense. All right, so if we want to show that it's not regular, then what we can do is, let's suppose that it is. So suppose L were regular. Okay, so and it's usually done by a proof by contradiction, which is what this is going to do. So here, if it were regular, then there must be a DFA for it, and that means that it has some number of states. And we represent this in a proof like this, with the number of states representing some number. So let's let P be the number of states in some DFA for L, because we know that it's regular by our assumption, so therefore there must exist a DFA for it. Okay, and the Myhill-Nerode equivalence relation is basically equivalent to saying show that P is infinite. And if you take a minimum size DFA, then if you show that the minimum size DFA must have an infinite number of states, then obviously there's no finite automaton for it. Okay, so if P is the number of states, well, what we want to do is we want to find a string that is of length at least P and is in the language. So it's long enough to where we must repeat a state, so it must have at least P characters, and you can show that it repeats a state via the pigeonhole principle, and it's in the language, so it's accepted by the machine. So we got to choose a string. Well, I'm going to call it W. Well, so one technique here is to stick this P right here into the exponents. So we can just say 0 to the P, but then the number of ones that appears after it must be follow this. So we can do something like P squared, and that would be enough. You could be you could put P squared plus P if you wanted to. So as long as this string is in the language and length at least P, we're all set to go. But I'm going to do this one. So one that I would not recommend doing is where we say, okay, I want to optimize the string, where I set P to be the number of ones and then square root P to be the number of zeros. So this is generally a bad idea because here, P might not be a perfect square, even though perfect square starts with a P. This might not be a square, unfortunately. So here, we don't need to, we can be a little wasteful here. In this class, we don't care about waste. There's nothing wrong with wasting strings. All right, so then here, what we want to do is we want to look at all decompositions. So look at all decompositions of this string right here into three pieces. I'm going to call those pieces X, Y, and Z. I think that's how Sipser does it, but such that the length of Y is at least 1, and the length of X, Y is at most P. And the neighbors are home. All right, so no comments. Okay, so this is true no matter what pumping lemma style proof you do. This will always be true. So the thing that trips students up is the word all there. So what we want to do is we want to look at every single possible way of breaking this string up according to these rules. Because if we forget one, then that might be the way to actually keep the string in the language forever. Whereas if we look at every single way and show that every single way gets out of the language, then we're done. Because no matter what the DFA is, it must obey one of those decompositions. And if we show that all of them don't work, then there's no DFA for it. All right, so let's see. Well, so this is not unique to this problem, but how we analyze the conditions is. So the X, Y length at most P, well, look at the first P characters of the string. They're exactly, they're all zeros. So that means that we know that X and Y consist of zeros. So X is going to be some number of zeros. I have absolutely no idea what it's going to be because we've got to look at every single possible way. I have no idea what way it's going to be. So, and I know that Y is going to be some number of zeros also. Again, I have absolutely no idea how many. All right, and then Z, since there are only 3 parts, Z must be the rest of the string because the first 2 parts are all the zeros at the or some of the zeros at the beginning, and the Z is the rest. So Z is going to be some number of zeros. I have no idea how many, and it's going to be all of the ones because X and Y didn't touch any of the ones. Okay, well, I have absolutely no idea how many these are. Might as well give them names. So when you have some concept and you want to actually name something and you don't know what it actually is, in computer science, we give that a variable name. So let's give these variable names. So let's use a different color now. I'm going to call the number of zeros at X alpha. You can use A or B or whatever, it doesn't really matter. I'm going to call the number of zeros in Y beta, to keep with the Greek theme here, alpha beta. The number of ones here is going to be P squared, because that's what we had at the start. And the number of zeros in the Z part is going to be P minus alpha minus beta, because we started with P, took away alpha, took away beta. Okay, well, here, now what we want to do is we want to pump out of the language. So that means we got to choose an I such that X, Y to the I, Z is not in L. Okay? And students usually trip over this about like which I to pick. So let's think. It turns out any value at least 2 will work here. But why? So why? So why does any value of I at least 2 work in this case here? Just this language. Might not be necessarily true for other ones. Well, let's see. Right here we said we picked the number of zeros to be exactly equal to the square root of the number of ones here. But if we pick I equal to 2, so just as an example, let's pick I equal to 2. Then that means we put another Y in. Okay, so another Y went into the string. Well, Y has length at least 1. So by putting another Y in, the length of the string got longer. Okay, so the length of the string got longer. Well, we know the Y part is only zeros. That's all it is. But then if we put more zeros into this string right here, that means that this side got longer, whereas this side, the ones, it didn't change anything. And so therefore, it doesn't obey this condition anymore because the number of zeros is now more than the square root of this. And so we have to actually prove that to be totally sure, but that's the reason why if we put more y's into the string, which only consists of zeros, we're going to put more zeros here, but not touch the ones here. And that's actually one of the reasons why languages like this are not regular, because we can have these runs where the counts depend on each other. Whereas if we had counts that don't depend on each other, putting more zeros into the string is not going to violate the condition, whatever it is. All right, so here, well, what is this string? So I can pick really anything that I want here, but as long as it leads 2. If I pick 0, then the condition only becomes more true, but I'm going to pick I equal to 2 here. All right, well, I'm just going to copy down the pieces. So I'm going to have alpha zeros, so this just says alpha zeros here. That's just copying this down, no difference. Then I'm going to have the y part twice, so because we said twice here. Then the z part, so p minus alpha minus beta, 1 to the p. Just copying down the parts. All right, well, let's squash all the zeros down. So the alphas plus alpha minus alpha, those get killed. Plus beta minus beta, those get killed. So at the end of the day, we have p, I don't have p plus b, I have 0 to the p plus beta. That's the number of zeros I got. And, oh, p squared. So I have p squared ones and p plus beta zeros. Okay, so I'm going to make some more room here. I hope you all are doing well. Okay, so what do we know about this string? So this is in L exactly when this is less than the square root of this. Okay, so that's exactly when this, square root. But this is exactly the same thing as saying that p plus beta is less than or equal to p, because that's what the square root of p squared is. And then if and only if we can subtract p from both sides, and then we'll get the condition that beta is less than 0. And this is a contradiction, because we said that the length of y, which is what beta is at least 1. Thank you, Frederick. Thank you for helping me pass my courses. You are very welcome. All right, so yeah, so this is actually a standard pumping lemma proof. I've offered it on a test before, so hopefully this is of use to some of you who are watching. Thank you all for your support. Any questions or any additional problems you want to see done? Yeah, because this was pretty standard, nothing too complicated. Hopefully we get to hear the neighbors upstairs dropping bowling balls onto the ground. That's what I imagine is happening up there. Haven't heard anything yet, so we might be in for a show though. Any questions about this or any other concepts you want me to take a stab at? And I should say thank you all for 500,000 views and a little over 7,500 subscribers, which is really awesome. We're going up, not as fast as other channels, obviously, but it's really dang cool nonetheless. What kinds of proofs do you want me to do? Do you have DFA problems? Do you have context-free grammar problems? Do you have Turing machine things? Decidable things, undecidable things, complexity theory things, if you're into that stuff. Do you have content about converting regex into logical formulas? It depends on the logic system so predicate logic. I don't have anything on that because I go off of the Sipser book, which doesn't have any of logic stuff. There is stuff about Presbyter arithmetic that I have not done on the channel, but it'd be really cool to do because it's a really nice application of using finite automata, and regexes are obviously equivalent to finite automata. That'd be really interesting, but I don't have any content like that, at least at the moment. I think we're done with this. No one wants to see a pumping lemma proof anymore. So there's actually something that I learned pretty recently, which I think is pretty dang cool. So let's say that we have this particular problem. And yeah, so what we're given is a DFA, let's call it D. And so that's one thing. The other thing is some integer k at least 0. And what we want to determine is the number of strings D accepts of length K. Okay? Okay. Let's see. So can we actually solve this problem, first off? So if I have a DFA, I tell you what the DFA is, and I tell you the length of the strings that I'm interested in. You can even replace this by like at most K or at least K. It doesn't really matter. But I want to know the number of strings that are accepted by that DFA of length K. So first off, is this a solvable problem or not? If so, then what's an algorithm for it? And if not, why not? Why is there no algorithm for this? Probably don't need this anymore. So is this thing solvable or not? Because the best answer for this is actually a very slick argument. It actually involves something that's actually really deep in what DFAs actually are. But is this thing solvable or not? Is this decidable or not? And the answer is yes. So this is solvable or decidable, with whatever term you want to use. And the general algorithm for this is just to run all strings of length k. And the running time, and just check whether or not the DFA accepts it and keep a counter of how many times the things are accepted or whatnot. And the runtime here, so the time complexity of this, is going to be, it's going to be exponential. So it's going to be 2 to the power big O of k. Okay, and times k, but that's going to be swallowed up in the notation. Because there are going to be exponentially many strings of length k. If the input alphabet is of length at least 2, has 2 characters in it, then the runtime for doing this is going to be exponential. So the thing is that we can do substantially better. Yeah, dear God, that's going to take ages. So the thing that's really nice about this is, what if I said, I don't want the number, I want the strings themselves that are accepted. So if I just took this off and I just said, I want the strings that are accepted of length k, then you really can't do better than this, because there theoretically could be that many strings, and writing the answer out is going to take that much time anyway. So it can't be much better than this. In fact, it can't be any better than this in the general case. Like if we had a DFA that accepts everything, then you really can't do better than this. If we wanted to output all the strings, but here we're interested in the number of strings. And that actually leads to thinking about, well, what is the size of the number? So the size of the number of strings, if we assume binary numbers, then that's going to be, the size of that number is the log of this at most. So we have a chance of getting a fast answer that way. It doesn't prove that there is a fast way of doing it, but it turns out that there's a really easy way. It turns out that there happens to be an easy way, it's just that this doesn't imply it. All right, so let's do an example. So here, what I'm going to do is I'm going to have a little DFA right here. So Q0, there's no meaning behind this DFA, it's just I gotta make one. So 0, 1, Q2, 0, 1, all right, so I just made some. Actually, let's make it a little more interesting. So I'm going to have it be 3 characters instead of 2. All right. So this thing has 3 characters in it. There may have been a comment. Let's see. All right. So here's the idea, which is actually really cool. It actually is based on some graph theory. Because if you think about it, finite automata are basically just directed graphs that have labels on the edges right here, the directed edges. And we can actually then think about, if we phrase this as a graph problem, I should just make this a little more interesting. So I'm going to make Q2 final also. So if I want to know the number of strings of length k that are accepted by the thing, that's essentially the same thing as asking, what is the number of strings that take Q0 to Q1 of length k, plus the number of strings that take Q0 to Q2 of length k also, and add those 2 numbers up. So that's an equivalent version of the problem. And we can actually use some graph theory to solve that. So what I'm going to define here are 3 matrices. So M0, M1, M2. Yeah, this should be fine. All right, so then what I'm going to do here is I'm gonna, so let's do M0, and I'll tell you what goes in each of these matrices. So it's gonna be a square matrix. If you know what an adjacency matrix is, then this will be basically is an adjacency matrix. Then what you do is, so I'm gonna label the columns by states. Oh, I should have labeled this. Let's call it Q3. I had two states named Q2. So let's label them the columns by the states, and rows are going to be the states also. Then what I'm going to do is I'm going to put a 0 or 1 in every single position here. Oh, thank you for the donation. Oh my goodness. Thank you, Jean. Oh, that's so nice. Thank you very much. Thank you, Vino, for your comment also. I didn't get to see that. Thank you. So what you do here is you will, in each of these positions, you put a 0 or 1, depending on whether there's a transition of that type. So notice that there is a 0 transition from 0 to 3. So in the 0th row, in the last column, I'm going to put a 1 there because there's a 0 transition, which is what this matrix is saying. We're only dealing with the 0 transitions here, from 0 to 3. So there are no 0 self loops in the entire thing. So the diagonal is going to be all zeros. 0 to 1, there isn't one there. 0 to 2, there isn't anything from 0 to 2. 1 to 0, there isn't any. 2 to 0, there isn't. 3 to 0, there isn't any. 2 to 1, actually I should have exactly 4 non-zero entries in here. So Q2 to Q1, there isn't any. 3 to 1, there is one there. 1 to 2, yes, there is. So, in fact, 2 to 3 should have one. Yes. Because there must be exactly one in each entry, and yeah, exactly one thing in each entry. So all the others are 0. Okay. Okay. So then we can actually do the same thing with M1. So instead of the 0 transitions, we do the 1 transitions. Okay, so then here, so I'm going to label these by the states again. So 0, 1, 2, 3. Are there any 1 self loops? Yes. So Q3 to Q3, that's going to have a 1 there because there's a 1 self loop there. And there are no others. So it's going to be zeros on the diagonal everywhere else. 1 to 0, there isn't one. Oh, yes, there is. Oh my goodness. That's embarrassing. 2 to 0, there isn't one. 3 to 0, nope. 0 to 1, yep, there is one right there. And this will actually carry with NFAs too. The same argument will work with NFAs. Because graphs themselves are inherently non-deterministic. There's no order of like which edges to pick if you're trying to look at paths and things. So it works with NFAs too. I'm just happen to work with the DFA here. Okay, so then Q2 to Q1, we don't have anything. And Q3 to Q1, no, we don't. It's hard to do an example on the fly here. Q0 to 2, we don't have anything at all. 0 to 3, we do not. Actually, there shouldn't be anything else in these rows. So 2 to 3 should have 1 there and 0 there. So we should have exactly one thing in each row. So let's do the final thing. And you would think, why the hell are we actually doing this? So then we're going to do the same thing with the 2 transitions. So Q0 is only going to go to Q3, so it's going to be zeros everywhere except there. Q1, where is it going to go? So it's going to go to itself, so it's going to have a 1 on the diagonal here. Q1 goes to itself on 2, and that's the only thing it goes to itself on. Q2 does the same thing, so it'll be on the diagonal. Okay, and Q3, what does it do? It loops on itself. So we have something like this. Okay, so unfortunately there's going to be one more matrix, and that's going to be the only other matrix, I promise, which is going to be the addition of all 3 matrices, just as integers. So just component-wise addition, that's it. So the top corner entry is 0 in all cases, so that's 0. We got a 0, 1, 0 here, so that's going to be a 1, 0, 0, 0, 1, 0, 1, so that's going to be a 2. And this one is going to be 1. Diagonal is going to be 1. So we should have each of the rows add up to 3 as a final check. So we should get a 1 here, and we should get a 0 in the last thing of the second row. In fact, we do. Third row, we should get a 0 here. Yeah, that's right. So then a 0, and I think a 1 and a 2. So 1, then 2. And then the last one is going to be 0, 1, 0, 2. So a lot of things in the last column. Everything goes to Q3. Yeah, so that should be it. So why am I bothering to define this matrix? Then what we can do is if we look at this matrix to the kth power, then this is going to be, so if we look at this matrix at row I and column J, then this is going to be the number of paths from I to J of QI to QJ, from the state I to state J of length K. Okay. So, and there's a good reason to see why that's the case. The matrix by itself is all the paths of length 1, because we just took into account the transitions. It turns out that if you think about, if you can actually prove this by induction by saying, if we look at the kth power and assume that's all the length k paths, then if we calculate k plus 1th power, then that just involves taking the kth power and multiplying it by this matrix. So matrix product. And if you analyze the entry of that, then it turns out it's exactly the number of paths of length k plus 1 from a certain state to another state. Okay, so then the answer to our question about the number of things that this accepts is going to be, so the answer in this case is going to be m to the k, the kth power, at the first row. So it's always going to be the first row because we're going from the start state and we want to end up in one of the final states. So this will be in the 0th row, and the final state here is Q1, so we want to look at 0, 1 there, plus m to the k 0, 2, because that's the only other final state. And that's it. So we could do an example here, but all you have to do is calculate matrix powers. And so let's think, well, how long does it take to do a matrix power? And I might as well put the old runtime up. So the previous runtime, which was the brute force method, so this was brute force, that was 2 to the power big O of k runtime. Well, how long does it take to multiply matrices? Well, that actually is a very delicate question to answer. But let's see. So it will be an easy answer is n cubed. So matrix multiplication, let's say, is big O n to the third runtime. So that is the number of states in the machine. So if we wanted to calculate the kth power, we would just do that k times. So it would be n cubed times k. So the new runtime is going to be big O of this. You can actually shave this to be big O of n something smaller times log k, which is a lot better, because you can actually take repeated powers of the same matrix. So here, oh, thank you, Jean. You didn't have to donate again. Oh my goodness. But thank you very much. But you can take repeated powers. So like for example, if you wanted to do like m to the 8th power as an example, you can calculate m, then m squared, then m to the 4th, because you can multiply m squared by itself, and then m to the 8th. And you can get there in 3 steps versus 7 or whatever. So the answer of matrix multiplication isn't really settled. There is an algorithm that runs in like 2.37 something runtime, which is not really practical. More practical one is like n cubed, or if you use Strasson's algorithm, you can get like 2.7 or something. But nonetheless, this is way better than this, because generally this type of question is based on the length of the string that you're given. So k is the really important parameter. The n is just based on the DFA that you're given. So here n doesn't factor into the runtime very much. So if n is way larger than k, then it actually might make sense to do this for some silly reason. But most of the time you're going to want to do this algorithm. So it's just taking repeated powers of matrices, because we can transform this problem into a graph problem, and then just analyze the adjacency matrix of it. There might be some things that you can do with spectral graph theory, which look at the eigenvalues of the matrices, but I haven't looked into that. Your free classes are better than most universities' lectures. The tuition bill is not always worth nowadays. Yeah, I agree. I feel bad about somewhat contributing to that problem because I'm teaching in such an environment, but there's not a whole lot that I can really do other than that. I mean, I gotta pay bills. There's not a whole lot I can do about that. Unless this channel goes really mega viral, which I don't anticipate ever happening, but if it does, then that'd be really good. Then maybe we can actually tackle the tuition problem, or at least address it, but sorry. Too bad there's not a way. Thankfully, you can learn stuff without a university education due to YouTube and other things, but it's just, you got to get a diploma to work. Why doesn't this prove P equals NP? This question of whether NFA accepts all strings or not is NP hard. It actually is P space hard. So let's see. The thing is, of whether an NFA accepts all strings, you kind of have to answer this question about K for a large number of Ks. All right, so you can do it. The thing is that the K parameter is going to be really large, and I think so. Let's see. Yeah, so I think the K parameter is going to win here, because in order for, let's see. Yeah, because that is an interesting question. Why doesn't that work? Because in principle, what you can do is just test the NFA on all strings of. Yeah, that is a really interesting question. There must be a reason why. So let's think. Why doesn't this solve P equals NP? Or P equals P space for that matter? Because I think the K parameter has to be substantial. Oh yeah, that's it. No, that's not right. Is it to do with epsilon transitions? It might have to do with epsilon transitions. Yeah. So in order to, you can't get this to work without epsilon transitions. Okay. And if you tried to collapse the epsilon transitions, then you need to make an NFA for the thing without epsilon transitions, and that requires, I think, exponential in the number of states. Actually, no, that's not true. That's not true. Yes, so let's write this down. That is a really good question. So the question of given an NFA, let's call it N, check if the language of N is sigma star or not. So one algorithm that you can do this. So this is NP hard. That is definitely true. So one algorithm you can do is convert to a DFA, complement the states, and then check if it's empty. The problem is that that'll take exponential time in general, to convert the NFA into a DFA. So the question is there a way that we can actually do this so there is another way you can check whether a DFA accepts sigma star or not. So an algorithm for checking if a DFA, let's call it D, has the language of D being sigma star. So one thing that you can do is to test all strings of length, I think it's at most, it's at most 2 times the number of states. The 2 here is to allow for a loop to go around. It's just for good measure. You can shave this a little bit, but it's basically twice the number of states. The 2 won't actually not be that important, but it's basically the number of states, and it's an exponential number of strings. So then the question is, so another way we can address this is to look at all the matrices. So I'm gonna take a look at m to the 1, m squared up to m2 to the number of states. And all of these can be computed in polynomial time. So we can store all of these in polynomial time. And then just add all the appropriate entries. And then just check if they, if the sum is equal to the total number of strings of that length. And the length and the number of strings of that length can be computed in poly time too. So the question is, why does that not work with NFAs? I'll have to take a look at that. Whoever asked that, thanks for the great question. I think it's due to maybe I said something wrong and that this does not work with NFAs. I'm fairly sure that it does. But there must be something that's going wrong there. That's a great question though. So whoever asked that, thank you for asking it. All right, let's see. Is there any other? Yeah. So the fact that there are non-deterministic choices, that doesn't imply it, because what we can do with the original matrix was to put a 2 or something, or the number of transitions on that particular label out. So effectively, the matrix here is just the number of labels that go out. Oh, that's it. That's it. Yep, that's the reason. I know what it is. So the important distinction here is that of the number of paths versus the number of strings, and those are different things with an NFA. With a DFA, if I take a different path, that must be a different string, because at some point we must have disagreed on a character. Whereas with an NFA, we can have something like this. So we can have 2 different paths that nevertheless read the exact same string. And that's the problem. So the NFA version will work in determining the number of paths, but not the number of strings. That's the trick. So it doesn't work in the sense that it doesn't give you the number of strings with NFAs. In fact, it doesn't work with NFAs with epsilon transitions, so maybe there might be a way to modify it, but yeah, so it doesn't work with NFAs for precisely this reason, because we can have multiple paths that have the same string. You can do something called a unique NFA, or I forget exactly. Oh, sorry, it's not unique. It's something called a UFA. So this is an unambiguous finite automaton, which is that for any string that you pick, there's exactly one path that I think there's exactly one path that the string could take from the start state, and for obvious reasons this will work here. So I think you can prove this type of thing with a UFA in polynomial time. With an NFA, this particular method won't work. Maybe there's some other method that will work. I have no idea, but yep. So that's the main reason. Cool. Any other questions? I think we've had long enough on a stream here. We had 2 really good problems here. All right, so thank you all for 500,000 views and 7,500 and now 7,600 subscribers. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. Thanks for supporting the channel. Thank you for Zhang and in your donations. That's very, very kind. You do not have to donate to the channel if you don't want to, but if you feel like this channel has helped you quite a bit, the links in the video description if you want to do so. So thanks for watching, and I'll see you next time. There will be a live stream in a few weeks. I'll send out an announcement about that. And then there will be at least one more live stream when final exams are about to come up. So I'll see you then. I didn't, I see what I did.